Welcome, hello, to this MariaDB OpenWorks 2023 presentation from Steven Senator at Los Alamos National Laboratory. You'll learn a bit about how Los Alamos uses MariaDB as part of its multi-cluster high-performance computing database project. And I definitely learned a few things about how they are maintaining and their service levels in highly distributed environments. Check it out.
Thank you very much for hosting me here. I'm here in fact, not because I'm a database person, I'm a database user, but I'm here to learn more from the people, you folks, and the other talks I've been to, the other workshops. But what I'm talking about today is actually deploying an application that is impactful, that touches a large part of the lab, and that is very affected by certain features that MariaDB has that not every other database has, at least not as robustly. So just a tiny bit about the lab and myself. I work for the High Performance Computing Division. High performance is perhaps an overused buzzword, but in this context, what it means is we build clusters. We build clusters that service our scientists and engineers. These scientists and engineers are physicists, are computational biologists, the kinds of folks who might do protein folding, are computational chemists, the ones who might look at the spread of diseases most recently. And these are not contrived examples, these are real experiments, real models and simulations that my customers use. We have approximately 18,000 lab employees. Of those, probably 12 to 15,000 use the high performance computers to run their models and simulations. Just a general outline of what I'm going to talk about, just a little bit on vocabulary. A lot of it will probably be redundant or things that you folks could even teach me about, but I'll talk a little bit about availability, services, service level agreements, how we use them on our particular application. I'll dive in a bit into our application's architecture and then start talking about the way it could fail, and then talk about some of the benefits of doing this. The specific measurable benefits and impactful benefits that we did. I'd like to start, though, by talking just a little bit about myself. The reason why is because this will help to communicate the criteria I use, the design philosophy, and how we ended up making some of the choices, both implementation and goals for this particular project. I started my career in many ways at Tandem Computers. You may or may not still see their computers around, but they do exist. They're running the stock market, they're running phone companies, they're running a lot of things. The three customers that I had a direct connection with and that made the most difference for me was what we would now call the old phone company, the Bell telephone system. The availability mattered to them not just because of risk, but also because, of course, downtime is noticed by everyone. And on Mother's Day, everyone wants to call. You need to be able to size your service appropriately. The stock exchange, of course, their availability mechanism is entirely different, and they really care because fractions of a second equal many multiples of dollars. And that last one was one I take particular pride in. That's kind of a push pin from a location map. For those of you who don't know, that's the flag of Kuwait. I'm particularly proud that our servers lasted throughout the Gulf War. The network and the country infrastructure may not have been there, but the computers came back up. The service was still available. And so it's quite possible, and in fact necessary, to build reliable, available services out of unreliable components. In almost every case, there comes a point where you can't afford as much as you really need, so you need to figure out algorithms that may be codified. in technology. They may even be hardened into your infrastructure, but often these are just algorithms of people, the processes you use to manage it, the algorithms you use to alert folks. Now, this is just a small level set about vocabulary. The first are the nouns, going from left to right. The fault is when some system is erroneous. Notice that it doesn't particularly manifest itself. It doesn't become activated until it's an error. An error means that you're not working according to your service level definition. That doesn't mean a human or an application knows it, though. By far the most important icon on that little cartoon there, it's the eyeball, of course. And these are not terms I invented. These particular ones are from a seminar back in 2009, but you can go through all of the industrial engineering literature to find them, to compare against factory design, going quite far back. Fault latency just to mention every bit there, would be the delay between a fault to an error latency from an error until an actual failure. Again, the failure is when it's noticeable by the end application or the human. So I was mentioning high performance computing. High performance computing, again, is just a fancy word, a fancy collection of words for a bunch of loosely connected computers that share some level of infrastructure. The some level of infrastructure in this context is a shared file system and a common mechanism that today we all like the word orchestration, but it's really a scheduler. A scheduler with just enough hooks so that an abstract virtual computer can be presented to each job. The context of this is exactly opposite to a cloud type environment in the sense that in a cloud environment, you always have more computational resources. You just have to put in your credit card and size it up. In a high-performance computing environment, you almost never have enough computation and resources to fully get your job done. So you're sharing, because the economies of scale of keeping all of those working together is more appropriate, is more dominant than just the ability to scale up your computational resources, scale up the network between them. One of the chief limiting factors, aside from shared storage, is simply the links between these nodes have to be low latency and high capacity. I can talk more about that perhaps in the questioning portion of this. I'm not going to read all this slide for you, but in terms of a scheduler, what we did is we decomposed the context of high-performance scheduling into about a dozen services, and as well as the traditional CRUD services. So things like a scientist submitting a job, things like that job getting an allocation of resources, then shortly thereafter, a job launching. All of these have slightly different signatures because if a human is in the loop, let's say Monday at 7:30 until the end of the day, you're going to have a different set of signatures of these jobs than traditional high-performance computing, which might be divided up into calculations that can take months and months. The COVID model I was describing is divided up. You heard in the previous talk about sharding. Well, in the high-performance computing environment, it's divided up into checkpoints and restarts. So a person may only get a day or 3 days or some limited amount of time slice, but then they will come back around with a subsequent job from their restart file. So in many ways, it's exactly like traditional scheduling, but with a modification of your time slice. Within a job, there are various stages that can be executed. This is just a traditional little time diagram, but humans submit the job. There's a delay between the time Of course, when they submit the job and when an allocation happens, ideally you want to minimize that, especially for the jobs that have humans in the loop, when there's active code development. Then there are multiple steps within a job, followed by accounting. I'm not including the CRUD steps in here. The steps in blue are the ones that actually go out and generate records into a database. So this means, depending exactly how people utilize the system, to how many different sub-steps, there may be multiple records, but in general, we are overloaded when we get CI/CD loads, not when we get, for example, a long-running job for tens of days or anything like that. It's sized by, for example, overnight regression testing. So just in terms of the actual application, well, let's look at failure modes based on some of those services. And I'll talk about some of these. What's interesting here, aside from the table, is just starting out, we both have to look at both planned unavailability and planned, and so we have designated system times, that's the DST acronym near the top, where we have quite a few different clusters. It's varied over my 10-year lifetime at the lab from around 12 to 15. We're in a consolidation stage right now for the same reason that everyone is consolidating into the cloud. It definitely makes sense to have an economy of scale, to have larger and larger systems, provided you also address mean time to repair and mean time to failure parameters. Of course, people like myself only tend to get these systems for approximately 1 day a month. Me tuning the system doesn't give bang for the buck, but my customers' work does. So it's important that we minimize the amount of time that we take the systems away from users. The other aspect is that we have clusters that go from about 30 nodes for maybe a departmental size experimental prototype cluster, a number of code development nodes code development clusters that are in the hundreds of nodes, 300 to 500 nodes. The workhorses tend to be 1,500 to 2,500. And of course, there's also the top tier ones, like our Trinity cluster right now, that has 20,000 nodes. And all of those have multi-cores. If you look at those, though, and that's important because the outages are multiplied by the number of clusters as well. If you look at the outages we've had just of the scheduling service since between 2017 and 2022, a 5-year period, what's interesting is of those 8 outages, 4 of them were because of initial storage. If you're looking at scheduling jobs, this may be true in the cloud, but it's certainly true in high performance computing. The biggest unknown is the workload submitted. We don't control what experiments the users want to do, whether they're doing a parametric sweep, whether today they're doing visualization to prepare for some milestone. So without knowing exactly what the load is, we have to make certain estimates about the capabilities. So from 2017 to 2019, we had 2 different clusters that didn't have sufficient storage. The top line on that table, GR, was our Grizzly cluster, a 1,500 node cluster, and we had to expand the storage for the job load we were getting. The next 3 of those cases were on Trinity. Trinity is a fairly large system. For a little while, it was number 6 in the world on the top 500. That's the one with 20,000 nodes, more than that in cores. And so similarly, we had to expand that storage. But by doing reflexive analysis and measurement, since 2019, we sized up the storage. That's why after that time, you don't see any of those errors. All the rest were ones that we fixed with process improvement, except for the one labeled Slurm control D, the second from the end. So these weren't, in the case of Slurm upgrade, Slurm's the scheduler, we were refining the process for doing an upgrade. When you upgrade a cluster, sometimes the database schema is updated. Sometimes it's tied to an OS upgrade because, as I said, we don't get the time to take the systems away from users for very long. So the Slurm upgrade was one where we had to fix up our improvement. The RPM dependency was another one where some person who perhaps should remain nameless, but he's speaking to you now, compiled the software with one compiler that was more convenient for the most recent experiment he had done, but in practice we needed to use a slightly different compiler with different features to deploy across all of the clusters. The third one, the accounting rollup, is the only one that was an actual vendor software bug. So this may be relevant to those of you who start looking at stitching together many different services from various components. It happens, I mentioned power failures and environmental pieces as part of the factors for our general environment. We don't have enough possible capacity to have completely reliable power. And if you get a power failure during the time when you're doing an accounting rollup, then subsequent accounting rollups could trigger an actual software bug. So it left the data in an inconsistent state from the point of view of the database. The final one was because our OS upgrade was coupled to the Slurm scheduler upgrade, which was coupled to the fact that in the OS upgrade, we were a Red Hat Enterprise Linux type of shop. And at that time, we went from using an initd old startup piece, because that's what RHEL was doing, to a systemd, and systemd is quite aggressive about timeouts. Well, unfortunately, those timeouts were not sized appropriately for doing, at the time, a relatively large job database and a database schema update. But we can and did address that in a slightly different way. I've mentioned this slide in some ways is a restatement of the previous slide, but I thought the data was more interesting than reading words at you. But this just talks about the various mechanisms we use to do both resource improvement. We sized up the storage. Process improvement, we completely automated our build process. And in terms of software, we added one feature to make sure that when we did encounter a failure that we became fail fast rather than load shedding. In some cases that may be relevant for applications deployed to the cloud. And we highly utilize students in order to address this, in order to do experiments with that. Okay. I'll come back to this when we talk about the customers, but basically by putting the data into this particular database, we also enabled the ability to pull out different signatures of different loads. If you have different signatures, then you can tell the difference between, say, the Monday morning human likely in the loop debugging session, those short small jobs, but where you might only get 1 to 3 of them for a given human sitting right there, versus the 10,000 or 20,000 that could be submitted from a CI/CD load from a GitLab, or even the traditional batch jobs where you might get just a long tail, but a large set of jobs, a large and long set of jobs. So I'm going to dive into just a tiny bit about our application architecture. TLCC in this, thank you, in this context, it stands for just, for this discussion, just traditional clusters. And so this is taken from the Slurm scheduling webpage. These are the user commands. These are the computational resources. Traditionally, there is a unification between the main scheduler and controller, adapting the protocols within the scheduler to the database, passing down to SQL. The Cray systems are slightly different because they're Crays, but also because they have very custom back-end networks within the cluster. So in that one, we factor out the database and put that adapter service inside of here. This particular project strongly resembles the Cray architecture. We are a conservative shop and we wanted to work on availability, so we're using this. However, I want to point out the spools here so that these lines don't become overloaded. We learned quite a few things, not the least of which was, again, that eyeball. Your monitoring and alerting makes the most difference. The service refactoring is critical whether or not you're using microservices. We factor out all of these onto individual physical platforms that were highly tuned specifically for the database. A large amount of RAM. This won't come as news to any of you. SSDs, RAID 10s, and a number of different tunings within the software layer, just TCP tuning, buffering, things like that. I'm going to skip fast through these, but taking a look at that architecture, you have to characterize how different components can fail. This is the traditional failure mode. With our architecture, then, we had to scale this based on different components that could be knocked out at various times, and how that directly related to our service level agreements. In addition, I mentioned that the servers were highly tuned. We have a primary to replica architecture. We're doing the replication live, but we also push backups between these nodes. The only difference between the primary and the alternate is its IP address. The replica is tuned for analysis and visualization. Also, I mentioned we only get the servers for about a day a month. So even though this says the word test is shorter and more convenient to type, that really means pre-production staging area so that we can push changes out there much in advance and then run virtual clusters using these for 2 to 3 weeks in advance before they roll out onto the primary servers. Okay, so with that in mind, again, alerting and monitoring becomes even more critical for this. I mentioned the pre-production pieces, and I'd like to revisit that table I showed you, but this is in terms of which components fail. So NICs can fail, but we bond them, and we are nowhere near the bonded bandwidth. So we've removed that error, we've removed that failure. You have to do alerting to know when to replace them, but that's a different issue. That database RPC to, I meant to go back to that, sorry. The database adapter, we just make sure that we can respond within 5 minutes. It's relatively easy to stop and start it. We have resilience in time of the service. In terms of if the database itself goes out, on the pictures that I perhaps came through too fast, you saw the queuing system. All of those that spool, we can handle approximately a day and a half database outage because of the size of the spool. That means that new accounts couldn't come in. But if you or have already submitted a job, a highly likely possibility, your credentials are already stored. So we don't have to go out and pull that live from the database. The first time, it's only when the accounting system it has a new user, a removed user, that we have to worry about that. If we have node outages here, again, we can flip between primary and alternate very fast. And we can also handle data center outages as well. I'll come back to this perhaps because that's actually an area of interest and improvement. I've mentioned the learnings we got out of this. But a large part of it is simply self-analysis, self-reflection, collection of the data, and a very aggressive alerting. I look with pleasure on some of the presentations that I learned from earlier today about how embedded that is in the pieces here. One thing I do want to point out, although we're exploring using things like max scale, exploring other resiliency features built into this, I work for a fairly conservative organization. The code that we are running is code that we are always running. We don't add extra code that only gets exercised from our test suite or from a resiliency test or a disaster recovery plan. That way, we know it's working because we're getting the alerts. We see it, we can monitor it live. Some MariaDB learnings, though, again, this is not news, but it's pieces that I wish to emphasize, that by keeping things directly in our infrastructure, you can get demonstrable benefits, ways that you can justify projects like this to your management, to any oversight people, even to just the monitoring infrastructure because you've built it in. It's immediate. Either you failed the test within the past 5 minutes within your service level agreement or not, and it's quantifiable. This is motherhood and apple pie. It's the same thing that you were seeing on earlier presentations. Similarly, refactoring to minimize the layers of code is critical. I happen to be talking about a project where we factored this onto physical nodes, but it's useful whether you're looking at the physical node, whether you're looking at infrastructure, whether you're making a lean hypervisor or an operating system, or whether you're simply doing this at the application or any of its libraries. This is relevant. And finally, and not the least at all, I want to point out that the reason I'm here, the reason the lab is a customer here, is because of the open source community good citizenship of MariaDB. I was able to characterize the software because it's open source. By characterize, I mean I was able to do security audits. I was able to vet it. I was able to compare it directly against many other alternatives simply because of that. In addition, I know that I am going to get relatively quick patches for CVEs for the same reason. If there's a vulnerability, there's a whole community that can contribute to this and has. That's part of why I have it. I'll just say one last word, and that's MariaDB backup. The reason why MariaDB backup matters to me, otherhood again of goodness, is simply that there was work done by the community to do very fine-grained locking. If you compare traditional MySQL dump to MariaDB backup, at least in our environment, you're talking about tens of minutes to do the backup for the data because of the fine-grained locking work. I can get a complete backup done in under a minute and usually be approximately 35 seconds. Without that, I could not hit my service level agreements. So I want to point out that the resiliency code is wonderful. Being able to burst into the cloud is wonderful. Don't neglect the core engine in your car. Just be able to have a performant database that you can back up and restore to hit your service level agreements. Thank you for your time.
Awesome. Thank you so much. We had a couple questions from the audience. One from online that they've been waiting on. The 20,000 node cluster you were talking about, they were curious what database product was being used. You might have answered this already and I missed it, but and then what kind of workload were you running, like OLTP, OLAP, HTAP?
Thank you for that question.
Yep.
If you Google Project Trinity and LANL, we could perhaps, if you can flip to that, you'll see that'll be a picture of the Cray instead of that conceptual diagram. That's actually using MariaDB community right now, but the successor system that's replacing it is going to be using Enterprise.
Awesome.
Could you repeat the details on the question so I can?
No, I think that was it. They were curious about the 20,000 node, and then what kind of workload was it? Like OLAP,
Yes.
OLTP, HSAP.
We have three distinct loads, and of them, the human-in-the-loop software development is what I was describing as the short, small job code development. Someone is doing continuous development of new physics, more complex physics, perhaps doing visualization. The other one is traditional HPC. Those are the long-running jobs as well.
Check.
And finally, the third load is CI/CD. That's the only one that maybe resembles OLTP because there's so many short, small jobs. Instead of, in this context, those would be sub 2-minute sorts of jobs that might exercise a new code development effort. That's growing, of course, like it is everywhere. But really, our traditional HPC jobs, the models and the calculations. What we do at the lab, we use computers to do something maybe not everyone here does. That's compute. And to actually do the calculations.
A couple slides back, I think in the refactoring section, you mentioned something about DST. I was just curious what that expanded to.
Designated system time, that's the time that we're allowed to take the system away from the users.
Not daylight savings time.
Not at all, no.
Any other questions, folks? We're running a little short on time, but that was some great content. So anyone, please just raise your hand. Okay. Yeah. Bring it.
Curious what version of MariaDB you were using in that Trinity cluster.
We're on 10.6 right now as I speak. I believe it's 10.6.7. We tend to track very closely for all the oversight and auditing reasons. I actually have a task when I get home to upgrade to the latest golden release that's been vetted by our security folks. So 10.6.12, I believe.
There was a question on, are you using max scale? But I think you answered that already. So
I'm experimenting with it. Yes.
Yeah, experimenting. Got it.
Yes. Yes, that is a very important factor in our environment. We have oversight and auditing regularly.